Consider the following example. I have a board, square or rectangular board with 4 pegs in it, and wrapped around those 4 pegs are 2 ropes that I pull on with given forces, 40 pounds on the rope going up and down and 60 pounds with the rope going left to right. And I'd like to calculate what is the total couple acting on the board plus peg system, assuming that each of the 2 ropes are individually in equilibrium. So this is a relatively complicated mechanical system, but if we're systematic about it, we can figure out what's going on. So let's start, as one should always start, with a set of free body diagrams. So I'll draw a free body diagram for each rope, and I'll draw a free body diagram for the board plus the pegs. Okay, let's start with the 60-pound rope. So I have the 60-pound rope with the 2 forces acting on the rope. So there's one and there's the other. And I also have a very complicated set of forces acting on the rope due to the pegs. And I don't really know very much about it, but I can figure out some things about it as we go along. And for the rope with the 40-pound forces, I have the same thing. I have the 2 40-pound forces, and then I have some complicated set of forces acting on the rope due to the pegs. Now, by Newton's third law, I have the exact same opposite forces acting on the pegs due to the rope. So over here, this guy here is going to match exactly with this guy over here. And likewise, this set of forces over here is going to exactly match this. And same for the other 2 pegs in the system. Okay. Now, I don't know very much about this complex interaction, but I know that this interaction has a net resultant force and net resultant moment. And that's actually enough to be able to come to a solution in this problem. So if I look at the equilibrium equation for the first rope, I have that the net resultant force and moment are equal to 0, and that's composed of 2 parts. 1, the pegs acting on the rope, and 2, the 60-pound forces. I can do the same thing for the rope with the 40-pound forces. There's the pegs acting on the rope, and there's the resultant force and moment due to the 40-pound forces. Now, the thing that I'm interested in is the action on the board plus peg system. So that's actually going to be the opposite of the pegs acting on the ropes. So I'll have this guy here. This is the opposite, so there's the minus sign here of what the pegs apply to the rope, and then I'll also have this resultant in moment with the minus sign also from what the pegs apply to the rope. So this is what I'm after. So let's go ahead and try and flesh this out a little bit more. So if I look at the rope with the 60-pound forces acting on it, I'll have that it's in equilibrium. It has the part from the pegs, and then it has the applied part. The applied part has 0 resultant force because the 2 forces are equal and opposite, and then has a moment, which I'll go ahead and compute about this point over here. So that's going to be 60 times the lever arm, which is 10.5. I've had to count for the 1.5-inch diameter of the pins. So if I rearrange this, I now know what the net resultant force and moment that the pegs apply to the rope is, and that's no force, but a moment of minus 630 EZ pounds inches. Okay, and so the opposite of this number is what the rope applies to the pegboard system. So that's what I'm really after here. And what allows me to add these 2 resultant force and moment combinations is the fact that I'm looking at pure couples. If I wasn't looking at pure couples, I would have to make sure that the moments were represented at the exact same point. But because it's pure couples, it doesn't matter what point I pick. So if I look at the rope with 40-pound forces on it, I have the exact same thing, and I can determine also that there is a pure couple of minus 540 about the z-axis, pound inches, acting on the rope from the pegs. So if I put those 2 together, I can get the total action of the ropes on the board plus peg system, and that now is going to come to me with a plus sign, 1170 inch-pounds about the z-axis. And it's a plus sign and not a minus sign because I'm using action equals reaction to get the final result.